Okay, so thanks everybody for waiting. So hi everybody and welcome to the ESA Challenges webinar. So thanks to be here. So today we are honored to receive the ESA experts to present their challenges. So for the history, ESA is the co-organizer of ActInSpace since the beginning, so since 2014. And we are going to present you ActInSpace quickly, make a little introduction, and after I will give the floor to the ESA experts. We are also going to make a Q&A session at the end of the webinar. So please feel free to ask all your questions during the webinar and we will answer at the end. Thank you. So I'm just switching off the camera to avoid all the connectivity troubles and have a good webinar. Thank you. So I'm going to start to present you ActInSpace. So ActInSpace have been created in 2014 by the CNES, and it's co-organized by ESA since the first edition. And they decided to give the operation part to the Aerospace Valley. So since the beginning, 35 startups were created and are still supported by our 16 international partners since the first edition. So here is a timeline of ActInSpace. So the first one was just a French edition, gathered around 12 cities. So the first international edition was in 2016. So we had 12 countries, 24 cities, 900 participants, and 40 startups were created. In 2018, we have 32 countries, 54 cities, 2,200 participants, and 18 startups were created. And in 2020, so for this first edition of ActInSpace, we have 50 countries from the 5 continents of the world. We are waiting for 100 cities, around 4,000 participants, but due to COVID, we think that it could be complicated, and we hope that more than 35 startups will be created. So the ActInSpace goal, so during 24 hours, the teams come together to work on challenges based on technology or data from space to event the tomorrow's new services and innovation. But ActInSpace is also to dreams during 24 hours and to dreams to become a future entrepreneur, to highlight the space sector and its daily impact on our society, to contribute to the social economic growth and to the startup creation also, to try to make a collaboration and the cooperation between the space and non-space companies on our society, because some subjects can be connected with space, like the agriculture or the environment and everything, and make patent licensing more accessible to all of you and to all the participants. So just a little history. Where did the challenges come from? So the CNES had the space patents hidden away for a long time, and they decided to make them accessible to all the participants of ActInSpace. So the idea was to develop the space and non-space sectors. Airbus just joined ActInSpace as a sponsor, and they decided to contribute to the challenges with data, and that's how the challenges were created. So the real bonus of ActInSpace is that by joining the event, you will have complete access to CNES patents if your goal is to create a startup or to develop a startup, and then you will have access after the event also. So it's a real bonus of ActInSpace. So I will now give the floor to Mercedes, and to present you the ESA. So, okay, I think you have the floor now.
Okay, thanks a lot, Matilda. Maybe just to introduce myself, my name is Mercedes Sánchez Alvarez, and I work at the Technology Transfer and Patent Office of the agency. and I wanted to give you today a quick introduction about the agency before the inventors present the challenges. So I will switch my camera. So for those who don't know ESA, we are an intergovernmental organization. We are composed of 22 member states, and we were created for the purpose of space development and technology, only for peaceful purposes. So we have 7 sites across Europe and spaceport in French Guiana, and the headquarters are based in Paris. You can see there the yearly budget of the agency. Maybe it's worth highlighting that 85% of ESA's budget is spent on contracts to industry in the member states. So to build a space mission, technology is needed that can handle the really harsh environments in space. So ESTEC, which is the ESA's technical heart, it's based in the Netherlands, and it's where most of the projects are guided through the different development phases of the projects. Here, what you can see in the picture is Europe's largest satellite test center, which is based in ESTEC. Because when you launch a spacecraft, both the individual components and the complete satellites, they have to be tested, because you need to ensure that they're ready for the really violence and of the launch and the vacuum and temperatures extreme of space. So in ESTEC, we have the biggest vacuum chamber, which is equipped with a sun simulator to reproduce space conditions. We also have the loudest sound system in Europe, and Europe's most powerful shaker table, which is equivalent to a major earthquake. So how can we? Does it move? Okay, so now that we can. No, it's not working. Maybe if I click here. Okay, here, yeah. So now that we can build a satellite, then how do we communicate with them? So that's where we have our Darmstadt European Space Operations Center. So once the satellite is put in orbit, the teams of the main control room, then they take control of the satellite. So there is always a flight control team, which is composed of many different technical disciplines, which control the different missions that are currently in orbit. So they can follow around 24 missions per year, and they of course have to do it 24 hours per day. And how do we, okay, again, yeah. So how do we get in contact with the satellites? We developed and maintain a ground station network, which includes some of the most advanced deep space antennas in Spain, Australia, and Argentina. And it's really, they are really needed to, especially for these space missions. So now that we know we can launch, that we can build, and then we can control a satellite, what do we do next? So ESA science missions have been exploring our planetary neighborhood to understand what is the planet's interaction with their host star, or to search for habitable worlds. So we have already sent some spacecraft to our closest neighbors like Mars, Venus, or Mercury. And in 2 years' time, we will send also a spacecraft to Jupiter and its moon to understand the evolution of the solar system. But then, of course, we also focus on astronomy with a fleet of missions, which are observing the universe across the electromagnetic spectrum, so from microwave to gamma rays. So I think what is important to understand with these last two slides is that this portfolio of past, present, and future missions shows the importance of the long-term planning in space. So, for example, the Rosetta mission, which I think is one of the most known ones to the public, it landed in 2016 on the comet, but it was first conceived in the 80s. So now we have to think where we will be in 20 to 30 years time. So the planning in space is really long term. So now we get a bit closer to Earth. This is one of the ESA's astronauts, Alexander Gerst, and he's in the International Space Station, which is the largest cooperative project in science and technology. And actually, we are celebrating now, the 2nd of November, we will be celebrating the 20th anniversary of the first crew going to the International Space Station. So I think the audience is highly composed of students. So if you were born in 2020, you've always lived with human life in space. So maybe you can always think, so what all these technology and developments impact or affect the people on Earth? So we have Copernicus, which is the largest Earth observation program in the world. It's run by ESA together with the European Commission, and allows us to look at the Earth with many different eyes, let's say. So not just by the optical, but we can see like wind power, a lot of different aspects of Earth. And it helps us, like, for example, disaster management and things like this. We also have developed Galileo, which is the most accurate positioning system in the world, but it's also used for transport services, including air, rail, road, and sea. And last, I think we don't have to forget that we live on a bit of a risky corner of our solar system. So in the image you can see ERA, which is a spacecraft that ESA is planning to test for planetary defense techniques. So together with NASA's DART spacecraft, it will assess if humankind has the ability to deflect the orbit of an asteroid. We also have some systems, for example, to watch the sun closely and to see if all the solar flares can affect the electromagnetic equipment on Earth. So to providing warnings about the possible flares and impact to the industry. So this is about ESA in short, very, very short. So I hope I was able to give you a flair of our activities. It's now time for ESA challenges. Maybe just the ESA challenges, of course, are based on ESA patents. In most of the cases, the idea is that participants build a business case around them, so finding what is the most promising application and developing a business plan. So what we're going to do is we have the inventors, who will be presenting the inventions to you. So please listen very carefully because they will try to explain you what are the key or the unique selling points of each of their patents. And this will give you hints to understand where these patents can be used on Earth. So with this, I will give the floor to David Evans, who will introduce the first challenge. Thanks a lot.
Okay, thank you, Mercedes. David, you should have the control. Thank you.
Okay, thank you. Let's try. There we go. Okay, well, thanks everybody. Yeah, I'll just follow on from Mercedes and explain my invention. It's of course is too short to explain in 10 minutes the invention itself, but I'll give you a brief overview of what it does at the functional level, and as Mercedes said, what the main points are. I'll stop the webcam just to save some bandwidth. There we go. Okay, so pocket size your data. It's called Pocket. It's the name of the invention. And let me see. Let's go to here. So in order to understand the invention, you have to understand a little bit about spacecraft communication, what the background of this is. So the first thing is that in spacecraft communication, it's amazing we can actually talk to our spacecraft at all, considering the power loss that takes place over millions of kilometers. What this results in is that bandwidth, so how much data we can download or upload, is a very precious resource. And of course, most of this is given to the application, the actual thing doing the job, and we still need to command and control the spacecraft. So the information that we use to control the spacecraft is called housekeeping data, and it's extremely precious. Yeah, so we need to make sure the missions work. Any small mistake can result in mission loss. At the same time, we don't get much data down, or we don't have much bandwidth available. The second thing to understand is that although spacecraft are quite advanced sometimes, their computers that we use for command and control have to be incredibly reliable. Like for instance, you expect your command and control processor to start up and work for 15 years without rebooting it. And you don't expect that from your iPhone or your PC or anything. And so they're not really computers. That's the first thing. They're more like microcontrollers, and they use embedded software, etc. And the result of this is basically it has very little processing power or memory available to do the job of what we're going to do. And the final thing is that we don't operate with all these normal protocols that you would have in normal communication systems. Things like TCP/IP and things like this are not there. We operate in what I'll simplify it called fire and forget. So basically, the spacecraft will send packets out or bits of data, and there will be no link back to say if they arrived or not. This means that basically we lose packets and they won't come back again. And so any compression algorithm must be robust to this, to losing bits of the information. So you can see straight away something like zip doesn't work very well, because if you lose a tiny bit of a packet in a zip file, well, then you can't unzip the file, just as an example. So why not use 7-zip or something like this on this housekeeping data? Well, the thing is that that housekeeping data is a mess, basically. Yeah? It's a mix of lots of values put together from a different unit. Say it's the unit which is looking at controlling the pointing of the spacecraft. And there will be lots of different values of where it's pointing, the angles, the temperature, everything all together, the statuses. And these are all mixed together, one after another. And this is the diagram that's trying to represent that. And basically, if you try and compress it with something big like 7-zip, if you know 7-zip is a very complicated algorithm, it will compress. So you get very good compression ratios, round about between a factor 10 and a factor 5 from the data out. However, because of this mixing of the data, if you try and use a simple algorithm, something which could run on a microcontroller type thing with very little memory and very little processing power available, well, it won't compress. Even worse, they usually expand. Okay, so it's not just a question of trying to find something which will compress the data. It's trying to find something which will compress the data using a very simple resources. And that's what Pocket Plus does. So this is the algorithm, the name of it. And it compresses housekeeping data very, very efficiently. In fact, it's better than WinZip. So, and it can do it basically using within those constraints with very little processing power and very little memory. And how it works is it takes these packets, they're called packets, bits of information together, which are streaming, and it takes each one and compresses it into a smaller one. So it takes each packet in. This is what the diagram's doing. It uses something called a mask, which I won't go into, but it's the concept, which is then the mask is updated continuously and automatically, and it produces a small packet at the end of it. So an identical packet, just smaller. Smaller means less bandwidth. So also, what about this? What if we lose a packet? Well, it's configured to be robust to X sequential packet losses. So basically, you can choose how robust you want your stream. Of course, robustness costs a bit of bandwidth, but it's only a little bit in return for some robustness. So you can set the thing up to say, okay, I run this and I'm okay as long as I don't lose 5 packets in a row, for instance. This is completely configurable. So it has this innate robustness in it, which doesn't exist for many other compression algorithms. And the second thing is it requires almost no knowledge about the packets at all in the stream. It doesn't care. In the software, the only thing that goes in there is the packet length. Yeah. However, it's not magical. Yeah. Well, what's absolutely required is that the packets that are produced are fixed. And what does this mean? It means that each packet has a fixed number of bits allocated to a thing, say a temperature or a status, etc. And that between the packets, this allocation of bits doesn't change. Yeah, I mean, this is where the mask comes in. So you need to be able to make a mask, and if things are changing all the time, then the mask doesn't work. Okay, so this is the requirement. So what's the main competitive advantages of it? Well, you can code this in less than 500 lines of C. It uses very, very low-level instructions, so there are no divisions, for instance, even in the algorithm. It's using ORs and ANDs and NORs and things, and this makes it very, very fast. So even on a microcontroller with almost no processing power, it's running really, really fast, and it doesn't use much CPU. Also, memory is not used, so it doesn't require, you don't need to build a file and then compress the file. Only a few, the equivalent of a few input packets are required to store it, and it works instantly. So as soon as a packet comes in, you can compress it, send it out again, the smaller one. There's this inbuilt robustness to packet loss, which is sort of unique, really. It has a good performance, better than WinZip, as you've seen on the data we have. And because we compress packets as they're generated, you can basically do whatever you want with the smaller packet. You can send it, you can stream it, or you could store it and then put it in a file and send that later. Yeah, okay, and the low latency is you don't need to wait for a certain amount of time. Okay. One thing to keep in mind is we're talking about bandwidth because this is what people involved in compression normally do, but it's a bigger story, really. So the first thing is that when you're an operator and you're trying to control something, like we're controlling a satellite, but somebody could be controlling anything in a submarine or an oil rig or a bunch of mobile stations or whatever, but they're controlling something remotely, and you have to allocate that bandwidth. If your bandwidth constrained, you have to allocate it carefully. And that means choosing which parameters you send in each different scenarios, how often the data comes, etc. This costs effort. So it takes effort, and this costs money, yeah? And you don't always get it right as well, so there's an element of risk. One of the things you're going to do, everybody does it because they're forced to, is parameters that don't change often. So if the values don't change often, well, you don't sample them frequently, yeah, because they don't change often. The trouble is that when you really need to know, because they do change, you also don't know fast enough. So the detection speeds can be lower than they should be, because basically you decide to save bandwidth. You were going to acquire this data every 1 minute or 30 seconds, whereas really you wanted to acquire every second. To counter this thing, so if you really need to know something, what you do is you set up traps. You say, if this value goes above a certain, if this parameter goes above a certain value, then send me a message immediately. Now, this is also takes effort. It takes effort to set those values. It takes effort to create the event messages. It takes effort to test it. So this is also a money and, of course, risk. You have to get it right. And also another nice thing is modern techniques like artificial intelligence, machine learning, anomaly detection, deep learning, all these sorts of new sexy algorithms. They're great. You know, you can use them on telemetry, but they don't work well on asynchronous event messages. What they want is regular, repeated, frequently sampled data, and they work better. So again, you're sort of shooting yourself in the foot of all that. So there you go. So if you can compress parameters, well, basically, if you can compress using Pocket Plus, you can basically, for parameters or values that compress well, you can send them as often as you want because it just disappears in the compression. And what you're doing there, you're simplifying the design because you no longer have to select which parameters you send, how often, etc. You reduce the testing effort. You put all the complication on the ground, on the post-processing of the data, instead of on the spacecraft itself trying to create asynchronous event messages and things like this and detection, etc. You detect stuff on the ground where it's easier, and also you can plug in modern data analytic tools, which are absolutely impossible to run on the spacecraft, but very, very easy to run on the ground. And the current status, well, we've already implemented on some flying spacecraft, Proba 2, OPSAT's been done. So it's working, and of course there's a compression part on the spacecraft and there's a decompression part in the control system. Both have been validated, and it's in the process of becoming a worldwide standard for spacecraft housekeeping compression. So we have an organization called the CCSDS that everyone's in it, NASA, JAXA, all the Russians, all the space agencies are there. And basically they've selected this, and they're world experts in compression, have selected Pocket Plus as the best way to compress housekeeping-like data, fixed data on a spacecraft. And it's supported, of course, by ESA, of course, by us, but also CNES. In order to get the CCS standard, you have to have 2 space agencies support it, and they have to implement it on the spacecraft. And we have CNES, the French space agency, are also supporting it. And that's the end of my presentation. Any questions, or I don't know how this works, but. Hello,
I think the
anybody
questions will come at the, yes, I think the questions will come at the end of the webinar.
Okay.
So the next, the next in line is Frank van der Hulst. So Frank, you can also go ahead with your presentation, please. Thanks.
Yes, good afternoon. If I can be granted control over the presentation, that would be excellent.
Yes, it's okay.
Okay, so good afternoon. My name is Frank van der Hulst. Let me see if I can navigate to my slide. Yes, so I will be presenting the hand controller device technology. I'm the inventor of the technology, patent owned by ESA, of course. So let me start off by introducing myself, and along the way I will actually introduce a couple of important concepts to understand for this technology. So for the past 10 years, I have been robotics engineer at ESA, and I have worked on a couple of very exciting technology developments. One of those technologies is space-to-ground teleoperation. So this actually means we control robots over a distance or systems over a distance. So imagine a user, in this case an astronaut, in the space station ISS, controlling a robot on ground. So we have done experiments to actually test this type of technology. Then I've worked on haptic systems, development of haptic systems for the space station. And haptics means the sense of touch. So with haptics technologies, we make sure that an operator is able to feel. So for instance, to feel what a robot is feeling. Then the third topic I've been working on is exoskeletons. Exoskeletons are systems that can be sort of robotic arms, but that can be dressed on by a human user. So the user is dressing on the exoskeleton, and all the motions that the user is making are being translated or coupled to a remote robot. So when the user would be moving his arm, the robot is copying exactly that motion. And also in return, when the robot is experiencing force interactions or touching something, this information is sent back to the user, and the user actually feels this interaction. And as a fourth point, I've been working on research towards intuitive telemanipulation. So again, I've spoken about teleoperation briefly. Telemanipulation is really targeted at manipulating something over a distance. So targeted at the functionality of the hand. So how do we control a robotic hand or a robotic gripper over distance in an intuitive way? And this is actually the research where the patent originates from. So after my time with ESA, I decided to found my own company, MF Robotics, and now we target development of haptic telemanipulation technologies specifically for robotic applications on Earth, because as we think, there is a lot of potential in applying such telemanipulation technologies for applications, for applications that may be all around us. So you've probably seen this, the brief, the ESA challenge number 6, give me a hand. This information, actually, I will go into it in much more detail on all the following slides, so I won't waste much precious time here. So let me get started on the original innovation and how it was developed for space. So, well, in space is dangerous. It's very dangerous. So, for instance, still, it's also technologically very complex. So often, for instance, on the space station ISS, people need to install new systems or payloads, for instance, on the exterior of the space station, or sometimes equipment needs to be repaired on the exterior of the space station, or maybe in the future we would like to do servicing of equipment, of maybe even satellites. Now, this is all very dangerous because space is very dangerous. You don't want to expose humans too much to the sheer danger of space. However, you still would like to keep the human in the loop, because what you are doing, the tasks that you are performing, are very complex. They require human intuition. They are maybe not very well defined from the start. They are not very easy to automate because of all this. So we were in search for technologies that allow still the human to be in the loop, the human to be in control of that task, but not to expose the human at the same moment. And this is why we need technology to control robots over a distance. Of course, this is space. You cannot tolerate failure or malfunctioning systems, so it's meant to be high performance. And in this case, since we are controlling complex robotics over a distance in complex tasks, you would like to put that human in real-time control. So at the moment that the human is making a motion, the motion should, as fast as possible, happen remotely at the robot. And when the robot is measuring data, it should be as fast as possibly reflected to the human. So 2 pictures on this slide. One is the NASA Robonaut showing a humanoid robot holding human-like tools. I think it would make a lot of sense to control such a robot using a human, because still it is a very complex robot and you almost need human capabilities, functionality to control such a complex robot, or otherwise you need to make very complex automation solutions that may not always fit the task. And then the other picture is showing the Interact rover as developed by the Human-Robot Interaction Laboratory back at ESA. And this system was actually controlled from space on ground. So it was driving on ground and it was performing tasks on this task board that you see at the bottom. So it's a task board filled with buttons and switches and connectors. And actually the astronaut over distance was able to perform those tasks successfully. So that is teleoperation from space to ground. Now to zoom into the patented hand controller device technology, it is important not only to control a robot arm, but also to control the end effector, so the hand or the gripper of a robot. So hand controller technology is meant to give a user control of virtual or real robotic hands or grippers over distance and to make you feel what that robot feels. And to give a bit of a better idea, there is a picture on this website, on the slide. It's showing the concept. So you can imagine sliding in your hand into that device. It fits in the palm of your hand. The fingers are resting on those movable elements. And those elements, they are sensorized. So they are able to detect motion and force that the fingers are exerting on it. At the same moment, there are actuators in this device. So those levers, those elements are able to provide force feedback to the fingers and provide resistance to the fingers. All in all, this allows you to make motions, make grasping motions as you normally would, while the device is providing this sense of force feedback. So reflecting the forces. And just for your understanding, this is one sketch, it's one embodiment, but of course, different finger combinations are possible. You don't need to have like a large lever combining multiple fingers. You can also have like independent levers or different configurations. And anyways, depending on your use case, the embodiment of a device may look completely different. Then it's also important to understand that such a device is not self-standing. It's part of a bigger system. So a teleoperation system in this case. Normally you would have a human operator controlling a distant task in a distant environment. And on one hand, you have the slave, the robot device to interact with the task. But on the other hand, you have the haptic device, the hand controller in this case, that the user is interacting with. Now this hand controller and the slave robot are being coupled by systems in between. So control systems, but also communication systems, depending on the separation of those two devices, the master and the slave. The controller and the communication systems can look quite different. So it's important to also look into basically the whole end-to-end system to support this hand controller technology. In terms of the unique selling points of the technology, the device is meant to be very intuitive, very usable. So it's a system really as simple as you grab the system and it's ready to use. You don't need to couple the fingers or constrain the fingers or calibrate the system. It's really, you grab the system and it's ready to use. And it's usable by a large range of different hand sizes. So small hands, large hands, male, female hands, it all simply fits on the device. Grab it and start using it. Then, since the fingers are not coupled, you are free to make grasping motions as you normally would while not holding a device. You're able to like move fingers independently, slide fingers, exclude fingers from the grasp even, do pinching with one or multiple fingers. So it supports very natural grasping motions, and this keeps the interaction ergonomic. And that's important if you envision endured use of such a device. Then another feature is the device is meant to be low complexity. That means as few actuators as possible, as minimum degrees of freedom. Keep to keep the device simple as possible, because if it would increase in complexity, it would increase in size, increase in mass, it would not fit the hand, it would become more unreliable or more failure prone. So this device relies on a minimum number of actuators and a minimum number of moving elements, yet supporting all those different grasping types by not coupling the fingers of the human hand to it. So I hope the previous gives a bit of an insight in what this device is, or what the technology is, and how this relates to the overall end-to-end system. So a hand controller device that allows to control a robotic gripper or a robotic hand over distance to feel what the robot feels, and how this makes part of this overall system where the human is using the device to control that slave gripper on the other side, interacting with this potentially complex task. So for space, development started in 2012. It started with, on a very fundamental level, and analyzing the critical functions and setting up experiments with this. Then a year later, we have looked into building the drive and sensor subsystem to validate if this actually would work in a laboratory environment. And since 2015, a project was started to implement this technology as part of a larger space qualifiable exoskeleton, an arm exoskeleton. So combining, or not only allowing the operator control over the hand functions, but also over the arm functions of a remote robot. And this is still ongoing, but I think it's in the rounding off phase. So hopefully soon there will be actually a full arm exoskeleton available to ESA. Now this is of course space application. We can envision many applications of similar technologies on Earth for like controlling something over distance on Earth, but also maybe to take a step back, this technology may be much more versatile than that. You don't need to control a robot over distance, or maybe you would like to control a virtual thing instead. But I mean, there may be very different applications possible even. And yeah, I'm very interested to see what comes out of the ActInSpace endeavors. So this was my presentation. Thanks for listening.
Thank you, Frank. Now it's the turn of Marco. So please, the floor is yours. Thanks.
Yep, thank you, Mercedes. I don't
You have
see
the control, Marco.
Sorry?
You have the control.
I have the control, yeah, but I don't see them. So how is it possible? Oh, here they are. Okay, so go back. Good afternoon, everybody. Okay, so I'm Marco Sabadini, and I've been an antenna engineer with ESA for something like 30 years. Before, I've been working on what it is today is Thales Alenia Space in Rome for another 5 years. So I've been essentially working my whole career in space antennas, designing all kind of different kind of antennas. So what I will be going to present today is a new type of antenna, and in fact the patent, which is the objective of the challenge, is devoted to the design methodology for those antennas. The reason of this duality will become hopefully clear during my presentation, so I will just go on. And this is an example of one of the implementation of the antennas. Now, this antenna is, let's say, a rather special one. This is thought to fly on a Copernicus satellite, one of the many which will be launched in the coming years. And the idea there is that somehow the satellite receives data from ground in observing the whatever phenomenon is looking at, the wind, the sea, the atmosphere, whatever, and then it has to send those data back to ground. And the antenna you see here is devoted to sending the data back to ground. As the satellite flies over ground, you need to point the beam that send the signal down to Earth to the ground station, which of course will be moving with respect to the satellite as the satellite moves with respect to Earth. So this antenna here is made of two parts. One, which is this disc, which actually rotates during the satellite flight and send the beams which points down to the ground station, and all the bottom part. And I invite you to see the difference between the antenna proper and the mechanism that moves the antenna, which is the bottom part, that actually implements the rotation. So one of the major targets for antennas, but also for any other piece of hardware which is flown on a satellite, is to make it as small and as light as possible. Room and mass are at a premium on satellites. Of course, the larger the platform, the heavier it is, and this raises launch costs and the complexity of designing the platform itself. And this as we move more and more toward using smaller satellites, it's even more compelling from the antenna point of view. Since antennas, unfortunately, unlike other devices, cannot be made smaller than they need to because of physics. So we really had to squeeze all the possible mass and size out of antenna, making it as efficient as possible. Metal surface, modulated metal surface antennas actually are very good in that respect, and I hope you will be understanding this in the rest of the presentation. The first point is that a flat antenna, so something which has a fixed shape, can produce a beam with different direction, so like a spotlight that points in different direction, and different shape. So you can imagine that your spotlight, instead of producing just being a spotlight, in fact, it projects some kind of shape. Actually, the development of this technology started quite some time ago, in 2006, and the first qualified model was built and tested in 2018. Now, where do modulated metal surface antenna come? Well, it's a long story, but I think the best way to look at it is to start from nature. Now, everybody knows what dolphins are, but maybe not everybody knows how the dolphins are able to swim as fast as they can. Now, the thing is that the dolphin skin is a very peculiar object. In fact, there is just beneath the top layer of the skin, there is a rather thick skin in skin terms of little ridges. You can see it here. And those ridges are not fixed, first of all, and second, they are oriented in a different way along the dolphin body. So what happens is that the water flow enters under the skin, the surface layer of the skin, which is porous, and is directed by those ridges and comes out of the dolphin skin later on the dolphin length, and this greatly reduces the resistance to motion in the water of the dolphin, and it makes the dolphin go fast. Now, modulated metal surface antennas work on a similar principle, but for electromagnetic waves, not for water. And so now I'm going to tell you more about that. And this is where actually the patent comes in very strongly, because to make the modulated metasurface possible requires a lot of effort in terms of design. So why the modulated metasurface antenna are very efficient? Modulated metasurface antennas are quite efficient because they can produce, as I said, many different type of beams out of simple and lightweight structure. The major point is that you can use this technology actually the same antenna, by changing just the surface of it to produce different type of beams. And making things a bit more complicated, you can even design antennas which are a variable beam. And there is another advantage, which is the fact that you can adjust the complexity of the antenna to the accuracy you need in pointing the beam, the loss of performance you can afford while the beam moves, and this sort of things. And this is very important because it makes you able to size your antenna to your application, instead of maybe having to use a fixed concept that fits almost any application, but then it might be very complex and very heavy. By the way, also the concept behind this possibility to be flexible on the implementation for antennas with, let's say, beams can be moved or changed in shape is being patented by ESA. So now let's go to how those antennas work. Now, if you think back to the first image I've been showing, there is this little hat in the middle. Now, you must imagine that the signal comes out from the inside of the antenna, and then this hat spread the signal all over the surface of the antenna radially. Now, what happened next is that, as we can see here, there are many, many dots on the antenna all around this hat, and the size and the precise shape of those dots make such that the wave that propagates on the surface will be radiated, and will be radiated depending on what you want to. So, I mean, it might be radiated only toward a direction, it can be radiated all around, depending on how you design this surface. And actually, in this picture, you see the currents flowing on the surface, which are related to the shape of the individual dots. And this is where the algorithm comes in, the methodology. The methodology enables you, starting from the kind of beam you need, to design point by point those elements. Now, imagine that those elements are much smaller than the wavelength, 1/10, 1/6 of the wavelength. So on an average antenna, you will have thousands or even tens of thousands of those elements. So designing them, and they need to be designed one by one in principle, is a tremendous effort. Now, what the algorithm does is to make this easy and doable, actually. So what is the major advantage? Then there are many others, but I think it's important at this point for the discussion to focus on the major one. Now, typically antennas are designed and built to produce a particular type of beam. And so essentially for every application, for every need, you will have a different antenna, larger, smaller, with different shapes and this sort of things. On the opposite, as I said already before, a modulated metasurface antenna can be designed in order to have a fixed shape, basic shape. So for instance, a disc, as we saw before, and then changing just the pattern on the surface. Now, in most implementations, this pattern, like the one I show, is just a piece of PCB. So different beam, different printing of a PCB, and that's it. You only need to change the master for the PCB printing, and then you have a new PCB with a proper, giving you the proper beam. And this is where the great advantage of this antenna comes. Now, as I already said, the backside of that is that the design of this pattern is very complicated. Actually, all the complexity of the antenna design is there in the pattern. And this is why the patent goes into that detail. So, why is not moving anymore? I don't know. Let's try like that. Where are we with those antennas? Well, in a nutshell, over the years, there have been a rather large number of developments, starting from the simpler ones to the most complicated ones. As I already mentioned, the PCB etching is possibly today the most effective way to build those antennas. However, it has been shown that those antennas can also be manufactured using 3D printing. There are limitations here, but with respect to the PCB printing, but indeed they can be done. So different shapes. For instance, here you see a horn which had a metal surface inside to produce very peculiar beam characteristics. And finally, metallic ones like this one, which is actually another antenna conceived for Earth observation satellite in the, let's say, Copernicus family. And this is fully metallic to support high power and to live better in a space environment of the low orbit where radiation is very strong and can damage plastics. And so this essentially concludes my presentation. Thank you very much.
Thank you very much, Marco. I think the next one in line is Matteo Tacola. So, Matteo, if you're ready, you can go ahead too. Thank you.
But we have the control of them.
I'm ready. I'm ready. Can you put my presentation on? Sorry. Ah.
Go.
You can control with the keyboard of your with the arrows of your keyboard. You can control the slides, so you can go to the next. Yeah.
Thanks a lot. It didn't work at the beginning, but now it works. So thanks a lot, and thanks for joining. I will give you a brief talk, and I think you have already seen what is the challenge. The challenge is to try to understand how you can move imaging spectrometers, how you can use imaging spectrometers, which are really an essential component instruments of a lot of ESA mission and space mission in general, and to find a way on a different field on Earth, because as we try to explain, hyperspectral instrument and imaging spectrometer are really widespread used everywhere in very different application, and they can find their way in really a lot of different possible solution and implementation. I will try to give a brief overview on that. And first of all, what is my patent about? My patent is about the optical design of a new family of imaging spectrometers which use a reflective grating. Don't be intimidated, I will explain it better later. And in imaging spectrometer is part of what we call an hyperspectral imager. And this is a key instrument for satellites in Earth observation, science mission, and so on. And what is new of my concept is the design is simple, compact, flexible, cost effective. And I wanted to write also beautiful, but then I didn't dare, but it is beautiful. I want to give a short background. Of course, you will note that we take advantage of our human color vision to understand what is the environment around us. This is from animals to humans, and this is from the prehistoric era. Nowadays, this is strongly enhanced by a very large quantity of different optical instruments, from telescopes, microscopes, and I'm always impressed every time I think about the numbers of people which have digital cameras with them all the time. If you think that around, let's say, 3.5 billion people are using smartphone, and smartphone they contain digital cameras. So really, now the optical instruments, the enhancement of vision, the elaboration of imaging is something that is going on and taking place at a rhythm which was years ago was not even believable. And what are hyperspectral imagers? This is just a specific branch of digital cameras that they take advantage and leverage on the spectral content of the scene. So when we talk about hyperspectral images and when we talk about digital cameras in general, we understand very well what is the spatial resolution. And here I'm giving an example of a satellite image with different space resolution from 8 meters, from which we do not really understand much, going up to 1 meter when you can see the structure of the street or of the trees, of the content of the scene. So the spatial resolution is what gives the possibility to understand the geometrical aspects of what you are looking at. And this is rather intuitive. But what about the spectral component of the scene? So let's go from the grayscale to hyperspectral. So let's imagine that we live in a monochromatic world and we try to go dressed to go to work like this, which looks like a perfect way. But then if you look at the color, you can really see that why the color is important. And you may laugh about this, but I found this picture in a website which was explaining what was one of the major disadvantages of people which are afflicted by color blindness. And this is the fact that, I mean, we live in a color world. Our way of elaborating information is based on the color information. But is the color enough? And here is an example of an animal which used the camouflage as a way of surviving to blend with the environment. And just looking by the eye, you might have a lot of difficulties to see whether this is the animal or the environment around him. So the color is certainly sometimes not enough, but each material has a specific signature, which is a spectrum, the reflectance spectrum, and this is specific for all different elements and material. You see an example here in this picture of a difference of spectrum between vegetation and green paint, and this makes you understand how spectral imaging has a wide range of application in remote sensing, because it is a non-destructive way of observing the world, and it can really recognize the components of matter. And this found its application in astronomy, agriculture, biomedical imaging, or even in this case in the camouflage, which is, I mean, why the frog they may deceive the world using the green color, but if you have an hyperspectral imager, you can always detect the difference of paint, green paint from a vegetation. And this also may sound like a joke, but this is a real application if you think about using hyperspectral instruments to distinguish between let's say a tank which is or a military component in which you put a green plastic bag on top to try to camouflage. So this is the importance of hyperspectral imaging, and from space we have a lot of different missions that use hyperspectral. I'm mentioning here FLEX, SHINE, EMMAP, PRISMA, which you can Google on and you can find a lot of more information. So basically, what is the basic principle? You have an optical payload, and I will explain a bit better how it works. This is mounted on a satellite, and the satellite has a certain SWOT of the imaging sensor. And the movement of the satellite, let's say, can get the other spatial information along track, along the movement of the satellite. And then for each pixel, for each point on ground, you also detect the spectrum. So what you have at the end is what is called in hyperspectral imaging is called the 3D hyperspectral cube, in which you have the 2 dimension, which is the spatial information, and then you are adding a 3rd dimension, which is the spectrum for all the pixels. And how is this important? This is found for space application, a lot of different applications. This is in agriculture, food, raw materials, for identify the species, to identify whether the vegetation is in good condition or not, whether it requires waters, what is the property of the soil. And this is, for example, the picture on top gives an hyperspectral map from which it is derived the organic carbon content of the soil. Or for the atmosphere, for instance, if you want to see what are the percentage of a certain gas in the atmosphere. So one of the next Sentinel mission, which will be used to map CO2, is it will use an hyperspectral instrument to really monitor what is the CO2 emission, and this is one of the most important for ESA mission for ESA in the future. I lost control. I cannot move to the next. Sorry. Hello? No. Oh, okay. So what are here in a nutshell? What is the component, the main component of an hyperspectral imager? You have a telescope which collects the light from the source, from the Earth. This light is focused on the entrance slit of the spectrometer, and this spectrometer, let's say, disperse the light in the different spectral components, which are then recorded on the focal plane. So this is the basic block of an hyperspectral imager, which is a bit more complex of a normal camera, because you need an optical element which performs the dispersion of the light. I'm trying to. So what is the spectrometer design in my particular patent application? This is made by just two optical elements, which is one mirror and one grating. So the light coming from the slit plane is diffracted 2 times by the grating and reflected 2 times by the mirror until it is focused on the focal plane. So this gives a very compact design with a full reflective solution, which is used to have a very large spectral range, and then it's also easy to manufacture and flexible, because you can have a different magnification between the slit and the focal plane, and it has an excellent optical quality. The main advantage with respect to the state of the art is the simplicity. I'm trying to show you what are different applications of spectrometer. All of these are instruments, that are concepts of design which are already flying. And you see that in general they use a lot more of optical components than just a single mirror and the grating. And this is the reason why the design that I was proposing is let's say, with a good advantage. What is the status of the patent? The patent is now in the design stage. So what we'll do in the future is to be embarked on a satellite, but also on a plane or on a drone or whatever different kind of camera application. It could be part of an industrial camera to check the food quality. Hyperspectral imaging is used a lot to check the quality of food. Or it could be integrated on the microscope. Why not? So whatever you think about the vision, you can enhance with the 3D dimension of spectrum, and then you can find an application for this kind of patent. So its future might be in your hands, and I wish you all the good luck to come with brilliant idea on that. Thanks a lot for listening to me. I think this concludes my presentation.
Okay, so thank you so much for all your brilliant intervention to all the experts. So we are now going to pass to the Q&A session. So please feel free to ask all your questions on the question box. So we have one first question. It's what would be the weight of the spectrometer? So I let the expert concerned answer.
I think that one is for you, Matteo. You need.
Sorry,
Yeah,
I was speaking with the mute microphone. Sorry. So the weight of the spectrometer, it depends on what is the size of the spectrometer, and the size of the spectrometer depends on what is the size of your image. So if you have a large swath of, for instance, I consider the application of a satellite. If you want to look at the largest swath on ground, then you need a very long slit in which you focus the light coming from the Earth. And then if you have a long slit, then your dimension of the spectrometer needs to be proportional by the dimension of the slit and needs to be quite large. If your field of view, what we call field of view, I mean your dimension of the scene is smaller, or also the spectral resolution, the spectral dispersion that you want to achieve is smaller, you can have a smaller dimension. So let's say it all depends on what is the application at the end. But it can be very small, or the dimension of a few millimeters, to the dimension of in a space application, the typical dimension is around 50 millimeter by 50 millimeter. So this is the typical dimension of the spectrometer, of the dimension of the optical things. Then you need to put a mechanical structure around. So let's say it goes by a dimension for a space. I'm talking about the space, typical space application. It will be a dimension of 100 millimeter by 100 millimeter, and the weight is a few hundred. It's a few hundred of grams. Is let's say a kilo, considering mirror and grating. Then, of course, if you consider the overall spectral imagery, in which you have the telescope and also the focal plane, it can go to several to few kilos. But if you need to have an application not for space but for on-ground application, it can be a very small dimension of, let's say, few centimeter by few centimeter, and the weight is the weight of let's say 100 grams, 200 grams. It all depends on the size. It really can be scaled to all kind of dimension.
Thank you so much. So another question, but maybe you already answered. Could you repeat the total minimum size and describe the dimensions more precisely? But I think you have already done it. Do you hear me?
Sorry, I again the same mistake. I was talking with the mute microphone.
Okay.
Can you? I think I have one dimension in one of my slides. If you can go back on that slide, maybe I can give a better indication.
Okay, wait. I'm just giving you the floor. Okay, now you are supposed to move to your slide.
Or you.
Yes, okay. Okay. Oui, c'est de remonter
You are moving, yeah, yes.
It must
you,
be around slide 3 or something like this at the other end.
Go down, 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 go down. Okay. Move, yeah, can you please, yeah. Go down, 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 down. This one, no, sorry, the one before, 55. 55. So you see, this is an application I try to do for a space payload, and you see you have the scale with 20 millimeters. So in this particular application, the overall size would be around let's say 100 millimeter by 100 millimeter by another 100 millimeter on the other. On the other side. So let's say typical application for a space of this very small compact. In general, you can go to larger size, but at least for a space component, it has a minimum of 100 millimeter by 100 millimeter by 100 millimeter. Of course, you can have also this kind of instrument which are attached to a drone, and there, of course, you can reduce to a smaller size. Going to a smaller size means that you cannot have the same dimension of the field of view that you can watch on ground, and you can probably make some compromise on the dimension on the spectral dispersion and on the number of spectral channels. But this is not, it has no limitation per se on the size. It can be scaled based on the application. This particular application, the typical size, it goes to in a cube of 100 millimeters.
Okay, thank you. So another question. So this one is okay. Could you give a rough manufacturing cost for the slit I see your diamond cutting is needed for manufacturing. Matteo, your sound is cut, or I don't know if it's Matteo who can answer this question.
Hello? Can you hear me?
Yes.
Yes.
Sorry, I missed the last question. Can you please repeat this?
Yes. Could you give a rough manufacturing cost for the slit? I see your diamond cutting is needed for manufacturing.
The slit, this is an excellent question, and the cost, it can be whatever kind of cost. I can tell you that if you are talking about a slit which is done for the space mission and the mission that we are doing at ESA, in which we need a really perfectly made slit, which really no defects, this can be also in the range of €1 million, but this I'm talking about a space mission. If you are talking about of an industrial application, you will have slits which are done by mechanical means, which might be not precise as the slit we are using and building for space mission, but the cost will be much more contained. The problem is that it might not be perfectly a perfect line slit. Therefore, it means that your projection on ground is not really straight. It might have some curvature that you need to compensate when you do the calibration, but this might not be a very big deal. So it depends on your application. The slit we use in the space mission, it might be very expensive components. But if you need to make a slit which is not perfect, because at the end you don't need the level of precision that we need for space mission, it can be a cheap component. Of course, it will not be a perfect slit, and this you will see in the image. But I mean, you have industrial hyperspectral cameras working with slit, and the cost is contained. I cannot give you a number, but certainly is not so big. If you need a perfect slit, it might be very expensive. In general, the most expensive part of a spectrometer is the grating, and depends on which kind of application you need. You might need a special grating. So if it is a commercial grating, also in this case, the cost is contained. If you need to have a special grating which doesn't exist, you cannot find it as an off-the-shelf component, but you need to have a company which is building the grating for you. This might be an expensive component. But if you take a grating which exists already from company producing optical components, and you just integrate it for industrial application, this is cheap. Can you read me?
Yes, thank you. So we have another question. So how much can the spectrometer cost to be used in a drone camera?
How much can the
spectrometer cost
yes,
to be used in a drone camera?
How much the spectrometer? Sorry, my audio is not so good, Mercedes.
Okay, so maybe the person will try to.
you're asking about the cost?
Yes, it was the cost, yes.
The cost is, as I say, the cost, it really depends on what are your application and what is the level of the cost. I mean, I have experience for a cost of space mission, but for space mission, we made everything really tailored for that specific application, and we want to have the best of each single component. So this makes the cost be really important for every kind of component. In this case, if you just have a spherical grating, which you can find on the market, if you go for companies doing industrial grating like Oriba or Zeiss in Europe or other grating manufacturing company which have already this kind of from the market. And if the spherical mirror is certainly not expensive, also if you find and you manage to put a mirror which exists on the market, then the cost is contained. Is few hundred euros. For a space application, the cost explodes also because we need the instruments that they need to withstand the vibration, they need to withstand temperature excursion and all these kind of things. But if you think about just a camera which is in your pocket and you take it or you put it on a drone to take some images, and you can realize the design based on off-the-shelf component, the cost is really contained.
Okay, thank you so much. Another question, how efficient is smartphone-based hyperspectral imaging? And what could be some of its applications? Thank you.
How much is efficient? How much is efficient?
Smartphone-based hyperspectral imaging.
How much is efficient to smartphone? Ah, smartphone based. Wow, that's a very brilliant idea. Guys, I have no clue. I don't know how you make. First of all, I don't know if they exist, and I don't know how that might be working. And considering the fact that a smartphone, you have a camera with a sensor which is integrated. In this case, you will need to have the camera with the spatial component which is attached to the sensor. So it would really need to make a smartphone which has this as a dedicated instrument. So it might be efficient, and it might be well functioning. The point is that I don't think that you can simply attach something to the lens of your smartphone to get an imaging spectrometer, because if you look at my presentation, one slide, what we have as a concept, the first element is the optical lens, which is taking the light from the ground. Then this needs to go to the spectrometer, which disperses light, and then to the focal plane or to the imaging sensor. And in a smartphone, you already have the camera and the imaging sensor, which are already attached together. So you will need to make a dedicated smartphone design based on that. And but it might be that in the future we will all have our smartphone with hyperspectral imaging, and we will go to the supermarket and we will take a spectrum of the apple and see if the apple is good or not, and we buy it. But for the time being, we are not there yet. So we have a small hyperspectral instrument, but this cannot be directly mounted on a smartphone, unless you find a way.
Okay, thank you so much. So we have some question concerning the presentation. Some people want the presentation, so the ESA will send us an email later to give us the presentation, and then we will share it with you, all the participants. So thank you so much, Fatio, for answering all the questions. So we are now going to close the session. So thank you so much to everyone. Thank you so much to all the ESA experts that we received today. Thank you for your participation and co-organization for ActInSpace 2020. And we wish you a good day. Thank you so much.
Thank you.
Thanks to
Bye.
you. Bye-bye.
Thank you.